Alright, today we're going to start our notes on conservation of momentum, specifically with bounce collisions. Now, conservation of momentum, when we're looking at this, you're probably reminded of our work and energy unit, right? Because in energy, we had different types of energy, and that energy was conserved. You drop a ball, gravitational turns into kinetic. Well, conservation of momentum, it's the same idea. Conservation of momentum is just saying the total momentum in a system is conserved. Conservation of momentum really is going to always apply, but the context that we're going to use conservation of momentum, the context that it's the most useful, is for collisions. In our definition of conservation of momentum, right, total momentum in a system is conserved. Well, what is a system? We've talked about this a little bit before, but just as a refresher, a system is really when you treat multiple objects almost like one bigger object. So if you had, say, let's do this in a color, maybe blue. Say you had object right here, object A, and object B. And let's say object A is moving and it has a momentum. Say it has a momentum of 20 kilogram meters per second to the right, in the positive direction. And maybe B is moving to the left, and it has a momentum. Remember, momentum is a vector. It has magnitude and direction. It has a momentum of negative 15 kilogram meters per second, of course, to the left, since it is negative. This is the momentum of each individual object. This is the momentum of A. This is the momentum of B. We could even add that in, right? This is the momentum of A, momentum of B. If you treat A and B as a system, that means treat them like one object. You're combining their values together. Their momentum, lost my place there. The total momentum then would just be adding the two values together. So 20 minus 15, your total momentum in the system would be 5 kilogram meters per second. So we're saying, with conservation of momentum, when we have our collision, that's when conservation of momentum is the most useful. When these objects collide, that total momentum, it is 5, right? Or 20 minus our 15, and after they collide, it has to be conserved. It has to be the same value. So what does this actually look like? Well, let's do an example. Let's make sure we're still recording here. Lovely. If we have a 2 kilogram cart moving at 0.5 meters per second on a frictionless track, runs into a motionless 3 kilogram cart, the 2 kilogram cart bounces back at 0.1 meters per second in the opposite direction. What is the velocity of the 3 kilogram cart after the collision? This is where we have to be careful as we're reading it. We're just going to fill in. I'm going to draw a picture. I'm going to draw everything as a box. I'm not an amazing artist, so instead of drawing a cart, I'm just going to draw a box. We'll start out with our first object, a 2 kilogram cart, moving 0.5 meters per second. It runs into a motionless 3 kilogram cart. Alright, 3 kilograms, and that velocity is 0. Excellent. We're going to set up a before and an after picture. We can even move this down just a little bit so that we can say, okay, here is before the collision. Then we'll separate our paper into two parts. Our right-hand side will be after the collision. Okay, so what happens afterwards? The 2 kilogram cart bounces back. So we still have our 2 kilogram cart, but now it's bouncing back. Be very, very careful with this. The velocity is no longer positive 0.1 meters per second. The velocity is now negative 0.1 meters per second. We're bouncing in the opposite direction. What is the velocity of the 3 kilogram cart? Okay, so we have our 3 kilogram cart right here. We don't know its velocity. Is it positive? Is it negative? Which way is it moving? That is our goal. We want to find out the velocity. How fast and in what direction is that 3 kilogram cart moving? To solve these problems, and really to solve all these different types of problems, when objects get into a collision, you are going to use the law of conservation of momentum, which is just saying total momentum in a system is conserved. So the total before the collision must be equal to the total after the collision. This right here, total before equals total after, that is conservation of momentum. We can split this up. We remember the equation for momentum. But first off, what is our total momentum, right? We're treating these objects as a system. So we could say, okay, instead of P total, this is really the momentum of object 1 and the momentum of object 2 added together. This is equal to, well, the total momentum after is just the momentum of object 1 added to the momentum of object 2. We're just treating them as a system, combining them. Now we can actually replace this. Right, momentum is mass times velocity, so the momentum of object 1 is m1 v1. The mass of object 1 times its velocity, plus m2 v2. Mass of object 2 times its velocity. Right-hand side, momentum 1, this is m1 v1, and m2 v2. Now we do have to distinguish. These aren't the same, right? We can clearly see here our first object, object 1, has some positive momentum. It's moving in the positive direction. After the collision, it's negative. Well, right now we have m1 v1 and m1 v1. These look identical. Let's change that. What we're going to do in momentum is we're going to introduce a new symbol. It's called prime, and all it means is really after the collision. So on our left-hand side, we have our before. This is m1 times v1. These are all before the collision. m2 v2 before the collision. Well, during the collision, the mass doesn't change, but the velocity does. Right, v1 over here is not the same as v1 over here. To distinguish that, we will just draw this little symbol. We'll do that on v2 as well. Again, what is this? This is a little symbol. It almost looks like an exponent of 1. This is a prime, and that really just denotes after. So how would you read this equation in red? This would be m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. What do those primes mean? It just means it's the velocity after the collision. It's just a little shorthand. You could even, if you wanted to, go back, add in those primes up here. This is momentum 1 after the collision, momentum 2 after the collision. Okay. Now we've got all our notation sorted. We're careful not to mess up our velocities, right? These are not the same. We add in that little prime to let it know, okay, that's after the collision. Now it's just a game of plugging in. The reason I like setting up momentum problems like this with our picture up top and splitting it down the middle and setting up very vertically is because it lends itself really easily to just plugging in. You have your first object, you plug in right here. Second object, plug in right here. Third object, plug in right here. Fourth object, plug in right here. So you can kind of just look up and take that information and plug it in, right? The mass of object 1 is 2. The velocity, 0.5. Mass of object 2 is 3. Velocity is 0. Then you say, okay, right-hand side. Mass of object 1 is still 2. So velocity is now negative 0.1. Again, that negative is so important. Be careful. Do not forget to make that negative since it's bouncing backward. We know the mass of object 2 is still 3, but we do not know the velocity of it after the collision. That's what we're solving for. Now, at this point, we're really just going to plug everything in and solve. This is just algebra at this point, so we'll go ahead. 2 times 0.5 gives us 1. 3 times 0 is 0. This whole thing is going to cancel out. We get 0. Right-hand side, 2 times negative 0.1 is negative 0.2 plus 3 v2 prime. At this point, we're just going to do really a few last steps to solve. We'll move our 0.2 over by adding it to both sides. This gives us 1.2 is equal to 3 v2 prime. Last step, 1.2 divided by 3 is v2 prime. This, of course, gives us that, 0.4 is the velocity of object 2 after the collision. It's a velocity, don't forget your units, meters per second. It is positive if our object our object right here, was going to the left, this value would be negative. That's how we know what direction it's moving. It's positive, so we're moving to the right. Okay. Now, that's really how you solve our problems. But to go a little bit deeper, there's a bit more with conservation of momentum that I want to talk about. Why is momentum conserved, right? We kind of just gave you the law. We didn't really talk about why it's conserved. That's what I want to do right now. All right, we'll start recording. Lovely. Calculate the impulse on a 3 kilogram cart. Remember, I stressed in class so much. Impulse is the change in momentum. They are the same thing. Impulse causes and is equal to a change in momentum. So really we're asking, calculate the change in momentum on the 3 kilogram cart. Okay, well, let's look at our 3 kilogram cart. We have it right here, and we have it right here. Well, we started, it was not moving. Mass times velocity, we did that right here. It had 0 momentum. In the end, we could calculate its momentum right here. How do we find change in momentum? Well, we know impulse is equal to force times time, but we don't have a force, we don't have a time. So that equation is kind of useless to us right now. We have to say, oh, there's another way we can find that change in momentum. Recall, change in anything is just final minus initial. Change in momentum is final momentum minus initial momentum. And at this point, you could solve for that final and initial momentum and get your value. Really, you could plug it in one of two ways. You could just plug it in right here and say, oh, I know this. Final momentum is mv final. Initial momentum is mv initial. If you want to continue rearranging, you can end up deriving the equation. Change in momentum is mass times change in velocity. I'll show you plugging it in both ways. Doesn't really matter which way you go about it. First way, plug in the final momentum. Well, final momentum is 3. Again, we have that right here. We know the mass is 3. What's the velocity? Oh, 0.4. 3 times 0.4 gives you 1.2 for your final momentum on that object. So we can write that out. Okay. 1.2 for your final momentum. What was the initial momentum? That's right here. It's not moving. Its initial momentum was 0. So we get your change in momentum, your impulse, being a positive 1.2 kilograms meters per second on your 3 kilogram cart. Let's do it the other method, right? Change in momentum is mass times change in velocity. Well, the mass is 3. The change in velocity went from 0 to 0.4. That is a change of plus 0.4. 3 times 0.4 is going to give you that positive 1.2. You get the same answer either way. It's just really how do you want to solve it. Okay, so in the end, our impulse on the 3 kilogram cart is plus 1.2 kilogram meters per second. I'm highlighting this is positive. The 3 kilogram cart gained momentum. It was at rest. It started moving in the end. Calculate the impulse on the 2 kilogram cart. All right, same process. Impulse is a change in momentum. Change in momentum is our final momentum minus our initial momentum. Look up at your 2 kilogram cart. What did you start with? Well, you started with 1 momentum. That's what we end up with down here. That's just the momentum of the first object. And that is our initial momentum, of course. So this is 1. What's our final momentum? Well, we calculated that as well. Right, that's right here with our first object after the collision. Mass of 2, velocity of negative 0.1. This is the momentum of your first object after the collision, negative 0.2. Okay, so your change of momentum, negative 0.2 minus 1, gives you negative 1.2. Don't want to forget those units. Let's make some room for them. Kilogram meters per second. Okay, so here, impulse on the 2 kilogram part is negative 1.2 kilogram meters per second. It lost 1.2 kilogram meters per second of momentum. Compare these two values, right? The 3 kilogram object gained 1.2 momentum. The 2 kilogram object lost 1.2 momentum. This is why momentum is conserved. In any collision, one object is going to gain some amount of momentum, and the other object is going to lose that momentum. In this collision, when they hit, the 2 kilogram object transfers momentum to the 3 kilogram object. The 2 kilogram lost momentum, the 3 kilogram gained momentum. It's almost like when you charge by friction, right? There weren't any electrons created, electrons transferred from one object to the other. Here, it's momentum transferring from one object to the other. Momentum is conserved because whatever momentum one object gains, in this case the 3 kilogram object gains momentum, that momentum didn't just come from anywhere, it wasn't suddenly created. The 3 kilogram object gained that momentum because the 2 kilogram object lost that momentum. So overall, in the system, if you look at both objects, in the system, that total momentum stayed the same. One gained, one lost, but the total in the system stayed constant. This is a really, really important process. You can see it in the math. You could go even further. Why does it have to be the case that the impulses are always equal and opposite? Well, let's look at that other definition of impulse we talked about, right? Impulse is a change in momentum, but impulse is force times time. Let's break this down. Impulse is force times time. In a collision, here we go. Here are two objects. They were moving, they hit. Here's object A. Here is object B. Object A applies a force on object B. This way. This is the force of A on B. Object B applies a force on A. This is the force of object B acting on object A. These are equal and opposite. Remember Newton's third law. If you hit your hand on the table hits you with just as much force, but in the opposite direction. So whenever there's a collision, the objects need to exert the same magnitude force in the opposite direction. Okay, so that means your force right here, in a collision, the force is always the same, but in the opposite direction. What about the time? Right? In a collision, is one object in the collision for longer than the other? No, the objects are hitting each other. If A is touching object B, B is also touching object A. You can't touch an object without it touching you back. So in a collision, both objects are in the collision for the same amount of time. The force is the same. The time is the same. I just did that backwards, but whatever. The force is the same. The time is the same. If these are both the same size, both the same magnitude, the impulse is the same. The only difference is that one force is in the positive direction, the other force is in the negative direction. So one impulse is positive, the other one is the same size, but negative. So momentum is always conserved in any collision.